Hey everybody, we're moving into 3.2 sum and difference formulas. I know that 3.1 is rather difficult, and I think those identities are more challenging to prove than the identities that you'll have to prove in 3.2. So hang in there. So I'm going to just do number two. I think rather than go through the proofs, I just want you guys to read through the proofs in the book. I won't test you on the proofs. And I'm also not going to expect that you know these by heart. So everything kind of up to now, except for I think it was lesson 1.5, some of those special formulas in there you don't have to memorize, but I want you to know up to this point. And now we're getting into some identities that I can't even remember for the like of me. So usually when you get into higher math, you've got your formula sheet and well, I don't know, some instructors require it, but I just think that the point, you're missing the point. So they want us to find all the values of sine A plus B, cosine A plus B, and tangent of A plus B. And we're going to use the sum formula of sine A plus B. So what we're going to do is we're going to expand it, first of all, using 3, 1, 2 right here. So you just fill that out, sine A cosine B plus cosine A sine B. And since I know that sine A for number 2 is equal to 8 over 17, I'm just going to do a bunch of substitution. So we have 8 over 17. Cosine B, which is right here, is equal to, so it's a multiplication thing. If you don't have to draw the dot, but that's what it is, 7 over 25, plus cosine A is equal to 5/17 or 15/17, and sine B is equal to 24/25. So you just finished doing all of the trigonometry. Now it's just cleaning this up. You can see that you have a common denominator with both of these. If you multiply this, this is a product of, what is that in my calculator? 425. So 425. 8 times 7 is 56, plus 15 times 24 is 360. If I add those together, the sum would be 416 over 425. Okay, so we just calculated the sine A of sine A plus sine B. Now we need to calculate cosine A plus B. And if I do that, I'm just going to use identity 313. So we have that that's equal to cosine of A, cosine B. Notice that in this one, it's cosine together, cosine and cosine, and now minus sine A and sine B. And then once again, we're just going to do substitution. So, and I'm on number 2. So cosine of A is 15/17 times cosine of B, which is 7/25, minus sine of A, which is 8/17, times sine B, which is 24/25. And if we clean this up, same common denominator, it would be 425 over 15 times 7, which is 105, and 8 times 24, which is 192. The only thing, did you see what I made a mistake of? This is a subtraction here because of this, right? So that is going to give me a negative value. It should be negative 87 over 425. Okay, so for tangent of A plus B, I'm going to use that special identity that we used in 3.1, that the tangent is the ratio of sine of A plus B over cosine of A plus B. And I found that sine of A plus B is 416 over 425 over negative 87 over 425. This is just a little lesson with fractions. In this case, if I multiply top and bottom by 425 over 1, do you see that those go away? And you might just already recognize that, but that disappears. You have one negative and you're left with 416 over 87, and it's fine to leave it like that. In fact, I prefer it as a fraction. Number 4 is very similar to number 5, and that's what you guys are assigned, and I'll talk about number 5 in a little bit. But it just says use the fact that 75 degrees is equal to 45 plus 30 degrees to find the exact value sine of 75. We're going to get into this with the unit circle, but the fact that sine of 75, it's not a convenient angle for us in the unit circle to calculate exact ratios with the trig ratios. So we do know, and I'm going to talk about this, what a 45-degree angle is and a 30-degree angle is, and we know how to find that. So I'm going to just set up a little triangle for both of those. So remember, theta in this case, if we have a 45-degree angle, we'll just call it this. And what I'm going to do is I'm going to let this point land somewhere where that the distance from the origin to this point is 1. It's just a convenient point. Remember, anywhere on this line for theta, the terminal side, you can have the point and the ratios will always be the same. So this is a 45, 45 degree 90 triangle. And just as a review, with a 45, 45, 90, if you draw it, you have 45, 45, here's 90. And so the two sides are, we can say, actually, the if the two sides are x, then the hypotenuse is x root 2. So this is a quick algebra refresher, a geometry refresher. So what you do is, if to find these two sides, you could guess and say what's root 2 plus root 2 is equal to, or by Pythagorean theorem, but you can also just do this algebraically and say x root 2 is equal to 1 because that's the hypotenuse, right? So if you solve, x is equal to 1 over the square root of 2. So that tells me that my two legs are 1 over the square root of 2 and 1 over the square root of 2. Now some books will keep it like this, and some books will write it by rationalizing the denominator as root 2 over 2. Okay, I don't mind you keeping it like 1 over the square root of 2, but be aware of both of these situations. So if I'll get to that in a second. I also want to talk about the 30-degree angle and why that's convenient. Notice with 75, if I were to, a little aside, if I were to draw 75, that's 75 degrees. That doesn't give me, and I drop down a perpendicular, that's 90. That doesn't give me any kind of special relationship. I don't have a 30, 60, 90 triangle or a 45, 45 90 triangle that I can work with and that I can find the lengths of all the sides. So that's why we break it up and can use these great formulas, the sum formulas, to make this work to our advantage. So now if we're going to do the 30-degree angle, now 30 degrees, and I'm going to drop a perpendicular down. So this is a 60, 30, 60, 90 triangle. Now on the side, this was in chapter 1, but if you have a 30, 60, 90 triangle, the smallest side is x, the next size is x root 3, and the biggest size is 2x. Okay? So in that triangle, if I say, okay, well, let's let this side be 1 again, the radius, remember, this is r when we're doing our ratios. That's the distance from the origin. So if I say, okay, I'm going to let 2x equal 1, then I can solve. So that tells me that x is equal to 1 half. All right. And then that tells me, so that's this side. So that's right here, 1 half. And then this side is 1 half square root 3, or root 3 over 2. So what I'm doing here is I'm kind of giving you an introduction, and you guys have kind of seen this, but we're going to keep doing it and get comfortable with the unit circle and all different angles of theta. Once you go from there, you can create this whole unit circle, and I want you to take a minute, Google the unit circle, get some images, and see what it looks like. You'll see these numbers come up, root 3 over 2, root 2 over 2, 1 half, and all of those. So from that, I'm going to expand this, and I probably should have done that first so that you guys can see, but I'm going to do it now. I'm going to use the sum, and they want us to find the exact value of sine of 75. So I can say that the sine of 75 is also equal to the sine of 45 plus 30. Okay, this is A, this is B. So when you expand it, I'm going to use the first formula, and I'm going to say, okay, that's the sine of the first angle, which is 45, the cosine of the second angle, which is 30, plus now it's the cosine of the first angle, which is 45, and now it's the sine of the second angle, which is 30. Okay, so now that we have all this information, remember it's this point right here from this is 1 over the square root of 2 comma 1 over the square root of 2, because I'm going over from the origin 1 root over root 2 units, and then I'm going up 1 over root 2 units. Okay, so that's your x, that's your y. The reason why I chose r equals 1 is we're getting used to the idea of the unit circle, but that makes it really convenient because now I can say that the cosine of 45 degrees is 1 over the square root of 2, and remember it's x over r, but what is r? R is 1. So really it's just cosine of 45 is equal to 1 over the square root of 2. So I'm just going to start filling these things in. Let me change colors. So I have 1 over the square root of 2 here. Times. Now the sine of 30, I'm jumping around. Let's stick with cosine here. So I also need to know the sine of 45, so this triangle here. So the sine of 45 deals with the y value going up. Sine of 45 is right here over 1. So that is just 1 over the square root of 2. Okay? The cosine of 30, we go to this and this point right here, I'm going over root 3 over 2. That's my cosine. That's always x in the unit circle. And I'm going up 1 half. So the cosine of 30 is your x. It's root 3 over 2. And the sine is 1 half. Okay? So if I clean this little fraction up, I have root 3 over 2 rad 2 plus 1 over 2 rad 2. So if you wanted to clean that up even more, you could rationalize the denominator. You can also just leave it. Root 3 plus 1 over 2 rad 2. Now, the cool thing about this is you could type in the sine of 75 in your calculator and get an approximate number. But this value right here, remember this is the sine of 75. This is exact, folks, which is really good. And we don't have to round. We know that this is the exact value and we can work with this value until the bitter end of whatever calculations we're doing. Okay, so we have another sum formula for tangent and difference formula. So 318 is the sum formula and 319 is the difference formula. And for number 5, it's the same kind of idea, except you have to use tangent. So you're going to say that the tangent of 15, and this isn't a sign problem, is equal to the tangent of 45 minus 30. And what you're going to do is this is going to be your A value, this is going to be your B value, and you're going to expand it using this formula. Okay, now to find 45 and 30, you can look at those triangles again and remember what tangent of 45 would be. If you recall, in our little units, circle, that's a bad, let's start over again. Let's do that. Okay, so here we go. We've got a 45, 45. So this was 1 over the square root of 2, 1 over the square root of 2, and this was 1. So tangent of 45 is y over x. So we can say that the tangent of 45 is equal to 1 over the square root of 2 over 1 over the square root of 2, which is equal to 1. Okay, so that's how you find the exact value. I'm going to let you guys figure out tangent of 30, but you just plug in those values. Expand this using the difference formula for tangent, and you guys should be able to do it. I'm going to do a couple more examples. Now we're going to prove a few identities. That's what the directions for this are. And you guys have the odds. So to prove this identity, it might seem like you want to start with this side, but what I'm noticing is that this, gosh, this looks really close to that, right? And I have this tangent of A minus B, right? So I think what I'm going to do is I'm going to stick with that idea. So let's roll with the left-hand side. We're going to start with the left-hand side. So what you do is you start with the left and you write it out. Whoops, not cosine. Cotangent of A minus B. And that's equivalent to, that's a reciprocal of tangent. So 1 over tangent of A minus B is the same thing. And well, gosh, I know what A minus B, tangent of A minus B is equal to. That's equal to 1 over, well, not 1 over, but it's equal to, it's in the denominator, tangent of A minus tangent of B all over 1 plus tan A tan B. And where is this going? Well, what happens to that? It flips the denominator. When you have a fraction like this, it's 1, the top, times the reciprocal of the bottom, right? So that just gives you, and I'm going to go down here, that gives me 1 plus tan A tan B over tangent of A minus tangent of B. Okay, the next step is that we need to change this into cotangent, right? And it doesn't look like cotangent right now, it's tangent, so that's not very helpful. So I know that this is not obvious to someone who doesn't do math all the time, right? So I guess just look for a trick. What you want to do with any identity is you want to maybe convert it to sine, cosine, or tangents, and that's what we did. We converted cotangent to tangent. Then you do a little algebra play and use the identities that are known. And then if I want cotangent, I want to get back to this, right? This is where we want to go, this side. So I'm noticing that if I multiply the top of the equation and everything in both top and bottom by tan A, 1 over tan A tan B, and that's okay to do. This is a little algebra trickery. Tan A tan B. That's okay to do as long as you do it to everything. Every term gets that tan A tan B. Okay, and I think just for this time I am going to expand it and take a minute to write it. So you have 1 over tan A tan B, because that's this times this, right? And then I have plus from beginning tan A tan B as well as tan A tan B, because that's what I'm multiplying everything by. And then I have tangent of A over tan A tan B. See, I'm really lazy when I do this because I just cross it off in my head, but it's easy to make a mistake, so be careful. And then you have tan A tan B, and then you get to do your fun crossing off, right? Because this cancels and this cancels. So that just gives you a plus 1 here. So we're left with the first term here is 1 over tangent of A times 1 over, I'm going to break it up just so you can see that this is actually cotangent A, cotangent B, right? Plus, this second term is just equal to 1. All over, we're running out of room. See how these cancel out? And I'm left with 1 over tangent of B minus, now we have the tangent of B's cancel out, 1 over tangent of A. Isn't that amazing? So you have on the top 1 over tangent A is cotangent of A, 1 over tangent B is cotangent of B, plus 1 over cotangent of B minus cotangent of A. And when you get through all of this, you take a breath and you go, did I get to where I wanted to go? Yes, right? Check all your A's and B's and your angles and your trig functions. Check. And then you get to say, quod erat demonstrata. I demonstrated that. For number 7, the example in the book is really good and it will help you. It's example 3.9, so see example 3.9 and follow that. The idea is that when you expand this, you're going to start with the left-hand side and you're going to treat this as one angle. This is like, think of that as just an A and then this is your B. So when you expand it, twice, and that should help you with that. Number 9 was very similar to what we just did with number 10, so you're set with that. And we're going to do one more example. For number 14, we're going to start with the left-hand side to prove this identity. I should put that prove the identity. That's the instructions. It's always good to read the instructions. So on the top, and I don't think I've even done an example with the difference. Here's the difference for sines. So it's sine A cosine B minus cosine A sine B all over. Now we have for sine A plus B, we're going to use this. And also get in the habit, 3.16, that's what this one is. And then this other guy that we're expanding, 3.12. So that is the sine of A, cosine of B, plus cosine A, sine of B. All right, so now we have to do some more math trickery. And once again, think about what the outcome is, what you want. You really want the right-hand side, right? That's dealing with cotangent. So how do you get cotangent with all of these sines and cosines? Well, remember that the cotangent of something like, keep doing that, the cotangent of B is equal to cosine B over sine B. So if I want that in my first term, how could I get? I've got a cosine B, right? I need a sine B underneath. So maybe if I divide this first term by sine A sine B, that would cancel out the sine A's. Do you see what I mean? And that might work for everything else. If you want cotangent A for the second term, you need cosine A over sine A. So that sine B, let me just write it down so you guys can see what I'm doing. So what I'm thinking is I need to divide or multiply by 1 over, same idea, sine A sine B on the top and the bottom. Note that this is multiplying by 1, so I'm not changing the value of the equation. I'm multiplying by one thing over the same thing. Okay, now I have to distribute this to everything in order for this to be fair. Okay, so I'm going to distribute that out, and what I'm going to do is I'm going to write it. I'm going to expand everything so it's nice to see. Cosine B minus cosine A sine B all over. I'm going to give myself space to write there. I've got sine A cosine B plus cosine A sine B. And then underneath everything, I'm going to put what I multiplied it by, 1 over sine A, so sine B. And I don't do this every time because I can recognize what I have left. So if you get it, I understand, I can follow your logic. But when you're getting used to it, it's kind of nice to do that. So you get to do your boom booms. I learned that from my math teacher. So what are you left with? In the first term, I have cosine B over sine B. What is that? That's cotangent, right, of B minus sine, which cancels boom boom, cosine A over sine A. What is that? That's cotangent of A. That's what we want, right? See, keep looking at what we're trying to get to, what our goal is. Cancel those out. Cosine B over sine B. What is that? That is, in fact, cotangent. Plus sine B's cancel out. We've got cosine A over sine A. So that's equal to cotangent of B minus cotangent of A over cotangent of B plus cotangent of A. Hey, we demonstrated that. QED. Have a good day.